Let's talk about vector projection. The vector projection of v onto u has the same initial point as u and v, and the same direction as u, and represents the components of v that act in the direction of u. So I'm just going to draw a picture that represents what this is saying here. So I'm going to draw two vectors. Oops. There's one, there's two, and I'm going to label them u and v. And now I'm going to draw how this computation actually works. So it's like dropping a line down to create a right triangle, and then drop that vector v down onto u. That's why I call it a projection of v onto u. And this vector is going to be here, and they call it PROJ with the subscript UV. And that's what it is. So it drops down in this way in the direction of u. And if we look down here, that's what we see here, is that we see that this is going to be a vector in the direction of u. And this is how we compute it. So that's going to give us this here. So that's kind of how that works. And then I can take the magnitude of it. And if I take the magnitude of it, of this projection of v onto u, I'm going to compute it this way. So that's what this means here, this magnitude of projection of v onto u. Okay, and then there's another component to it, that if I take that magnitude, I can also call it a scalar projection. So that magnitude is called a scalar projection. So you can see that language, you can see, find the magnitude of the projection. So those are the same thing. And as you can see, it's the same formula. Okay, so let's get started with this one now. Let's take one. So let's look at this here. So essentially what I want us to do here is draw the vectors first. So this problem says find the projection of A onto B of the vector A and the vector B here. And all I want to do first is graph these. So in the graphing of these, we have -1, 2, and 3. And I'm just graphing vector A first. So I'm just going to kind of run these out a little to kind of get an idea of where my points are going to be. So I'm going to come off the Z now, and I'm going to run it to the back there, and then run the other one up. And my point, my terminal point, should be about here. So now I'm just going to draw a vector for that. So there it is. And now I'm going to draw the other vector, vector B. So for this one, my X would be 3, so that would be here. My Y would be 6, and my Z would be 8. And then I'm just going to kind of walk the X over to where the Y would be. Bring the Y up now. And then bring the Z straight across. And remember, I had to go up 2 more from that. And then now I'm going to bring the X up to the Z. And then I'm just going to kind of take that over. And then just to kind of get an idea of where that terminal point's going to be. And it'll be here. So now I'm just going to create the vector for that one. So here it is. Now my projection is A onto B. So my A function is the green one, and my B function is the orange one. So I'm going to label those now. So this is B, and this here is A. And I like the different colors here. It's kind of nice to be able to separate. Okay, now all we're going to do is our B, A is going to be projected onto B. So it's going to kind of come up this way here as a right angle. Now we can't really see that right angle because it's facing towards us, but let's say that's a right angle. It'd probably come more this way, and then this would be the vector I'm looking at. So one thing I can see right away is that the projection of A onto B is going to be parallel with B, because they'd be in the same direction or opposite directions, remember, for parallel vectors. And it's also going to be a scalar of it. I should say like I would be able to get from vector B to the projection of vector A onto B by just multiplying it by a scalar. That's what it means to be parallel. So let's take a look at this. So that means that scalar is going to be less than 1 here, because think about this. This thing looks like it just drops down below it. Now again, this is just by a picture. 90 degrees could be way over here and it actually be bigger than it, but we're going to find out what that looks like as we compute it. So let's take a look back at the formulas here. So this is the formula we're going to use down here because we just want to find the projection. So we're just going to take that formula and put it here. And that's that formula. Notice I only took the second piece of it. That's the formula we use most of the time when we're finding the projection. They gave us 2 formulas here. This was the other one. We don't use that one as much. This is the one we're going to use here. This is simpler to plug everything in. It's less computations. So this is the one we're actually going to use here to find this projection. Now again, my end result here is going to be a vector, and this one's going to be in the direction of u. And for ours, since we're doing a projection of A onto B, that means our u then is going to be our B. So let's just set it up to what we're using here. So let's see what our projection is going to be. So we have a projection of A onto B. So my B would go down here. My A would be here. And that means this is going to be my U, again, being B. So I'm going to have vector B dot vector A over the magnitude of vector B times, oops, put my U in, vector B. So there's our setup. And from here, we're just going to find all the necessary components that we need and plug them in. So first off, we need B dot A. So again, with those vectors, I'm just going to put them in there. So that's going to be 3, 6, 8, dotted with -1, 2, and 3. Now I'm just going to race through these calculations because hopefully we're getting a little more comfortable with them by now. So this is -3 plus 12 plus 24, and that equals 33, because this is going to be 36, and then -3 is 33. So that's what our dot product is. And then our magnitude of B, oops, not P, but B. Okay, that's going to equal 3 squared plus 6 squared plus 8 squared square rooted. And that's going to result in square root of 109. And that's our magnitude of our vector B. And then all we're going to do is times that by our vector B. So that's going to result in, so my dot product was 33. My magnitude of B was square root of 109. And my vector B is 3, 6, 8. So there it is, and I can multiply it through. And simplifying, I'm not going to be able to, because square root of 109, I can't get anything simpler than that. And I don't have to go any further than that, so that would be enough. So I would get, for the first one, we would get 99 over square root of 109. The second one, we would get 198. Oops, let me fix my 9 there. 198 over square root of 109. And then for the last one there, 264 over square root of 109. And essentially I just took that 33 here and just multiplied it by each of these. There's nothing more I can do than that. So our final answer for this projection is here. Now, one thing that's interesting here, though, before I sign out on this one, is the fact that this number I multiplied by vector b, this number here is actually a little larger than 3. It's 3.16, which tells us by our drawing that this a would actually come past vector b, actually quite a bit further than it once it reached it with that projection, and that would actually be a little more than 3 times a vector b. So that would definitely be off our paper there. So it's just interesting that we can't really see that here, but just the idea of what's really going on.